Today we will be summarizing fluid properties on the notes that I had sent you. So if we go into fluid properties, there are different properties that we need to take charge of. The first one would be your density. Second one would be your specific weight, specific volume, specific gravity, viscosity, which is also then subdivided into two, which is your dynamic viscosity, which is also your kinematic viscosity. And then there's the cohesion and the adhesion, which I would leave to you for self-reading. There's also the surface tension that I would leave to you for self-reading. Then there's the capillarity. There's the compressibility, which is also then for self-reading. And then, of course, we have the units of measurements. Now, I want you to do self-reading on the units of measurements. We need to find out what would be the fundamental units. And then we would also then know what is the derived units. We would also then go into the forces that's causing the fluid motion, which number one would be your gravity force. Number two would be your pressure force. Number three would be your surface tension force. Number four would be your viscous force. And then number five would be the compressibility force. And the last one would then be force due to turbulence. So just again, bear in mind that the forces that's causing the fluid motion is your gravitational force, it's your pressure force, it's your surface tension force, your viscous force, your compressibility force, and then all the forces due to turbulence. Those would be the forces that would be causing the fluid motion. We would now go into each of the specific fluid properties, where we will then look at the units, we will look at the equations, and from there we would then work out a couple of examples. The first fluid property that I would like to look at is the density. Density, and we have the Greek symbol there that is rho that we will be using for the density in fluid mechanics. And we know that from the definition of density, we know that density is equal to your mass per unit volume. So the equation then that we're sitting with is rho is equal to m over v, which is your mass over your volume. And we find out that the unit for density would then be kilograms per cubic meter. So that would then be the equation for your density. The next one would be your specific weight, which is your W. And so if we look at the W, we're sitting then with W is equal to, or rather your specific weight is equal to the weight of the fluid divided by the volume of the fluid. Now, if we have the weight of the fluid, we know that weight or force is equal to mass times gravity over V, and we find out that that would be newtons per cubic meter. Why newtons? Because we find out that mass times gravity is newtons, which is a force, divided by the volume, which is cubic meters. So if we derive the equation, we would simply say that m divided by v, that is the same as your density times gravity. So therefore, the simplified equation then for specific weight is equal to gravity multiplied by your density, and the unit there would simply be newtons per cubic meter. The next one that we will look at is your specific volume. So your specific volume is simply your volume of the liquid divided by the mass of the liquid. So you can see it's the inverse of your density that we have there. And so therefore, very simply stated then, that your specific volume is equal to your volume divided by mass, and that would give us then cubic meters per kilogram, which is the inverse of your density. So remember then that your specific volume is the inverse of density, and that is 1 over rho. Your viscosity, as I have said, is divided into two types of viscosity. You have your dynamic viscosity and you have your kinematic viscosity. So looking at the dynamic viscosity, it's a U. The symbol is a U with a tail to it, which is normally termed as mu. Mu is the Greek word for your kinematic viscosity, and your kinematic viscosity in terms of an equation is equal to your shear stress divided by your change of velocity by your change of distance. So if we put that into an equation, we simply say that your dynamic viscosity is equal to your shear stress, which is tau, divided by your change in velocity divided by your change in distance. So if we see shear stress, the unit for shear stress or the unit for stress is newtons per square meter, which is your Pascal. And if we derive and simplify du by dy, we find out that that is second. So the unit then for your dynamic viscosity is either written as Newton second per square meter or Pascal second. Not per second, Pascal second. So that would then be the equation for your dynamic viscosity. Again, shear stress divided by your change of velocity over your change of distance, tau divided by du by dy. Your kinematic viscosity is a skewed V again, and that is nu. So we have mu and we have nu, the Greek words. And so if we go to the kinematic viscosity, we find out that your kinematic viscosity is equal to your dynamic viscosity divided by your density. Your dynamic viscosity divided by your density, and the unit for that is square meters, sorry, not cube, square meters per second. I want you to derive this unit, square meters per second, from your dynamic viscosity and your density. We said that your dynamic viscosity is Newton second per square meter. We know that your density is equal to kilograms per cubic meter. So having divided those two, see whether you get square meters per second. Another equation that we use in terms of your kinematic viscosity, because viscosity is dependent on temperature. So therefore, if temperature then comes into the equation, then we need to find an equation that has temperature in it. So we find out that your kinematic viscosity is equal to 497 times 10 to the power minus 6 divided by 42.5 plus t brackets to the power 1.5 square meters per second. The T in the equation there is your temperature in degrees Celsius, not Fahrenheit, not Kelvin, degrees Celsius. So if I give you a question and I give you the temperature in terms of degrees Celsius, you first need to then calculate the kinematic viscosity before you do anything else. So that would then be the kinematic viscosity. If we look at capillarity, there's an equation in the textbooks that simply says H is equal to 4 sigma cos theta WD. Now again, H is the rise or the fall in the capillarity tube is equal to 4 times sigma times the cos theta divided by WD. The W is specific weight and the D is the diameter of the tube. Now just looking at the sigma and the theta, we find on page 17 that I had sent to you that your sigma is the surface tension of the liquid, which I said that you had to read through, and then also your theta is the angle of contact. Now, these two figures in the textbook on page 17 is very important, because we find out that if you have a liquid in a bowl and you insert a tube, you'll find out that the liquid would rise in the tube, and we find that that is your capillarity that occurs there. So if your angle theta is less than 90 degrees, and if you see where theta is measured, it's from the tube to the extended capillarity line, and so that is your angle theta. If it's less than 90 degrees, then we're looking at something in terms of there would then be a rise in the tube, or H would be positive. If there's a drop in H, then we find out that your angle theta, or your angle of contact, is greater than 90 degrees, and so therefore your H would then become negative. So what I have done in my textbook, I've said for the angle theta to be greater or equal to 0 and less than 90 degrees, H is positive. Where theta is greater and equal to 90 degrees and less than 180 degrees, H is negative. And so therefore, if I do not give you any values for the angle of contact, these two are very important for you to remember. The value theta for mercury and the glass tube is 128 degrees. So that angle there would be 128. So again, if that is greater than 90, then we know that your H is going to be negative. And then for water, we find out that for water and the glass tube, the angle of contact is 0 degrees. So if that is 0 degrees, then your H would then be positive. So from the above equation, it is clear that the capillarity action is inversely proportional to tube diameter. Smaller the diameter of the tube, greater will be the capillary action. Recommended minimum tube diameter for water and mercury is 6 millimeters. So that would then conclude the fluid properties that we need to look at, except for the 2 or 3 that you need to read through on your own. If we work through one of the questions found on page 25, the first one reads as follows. Calculate the specific weight, the density, specific volume, and specific gravity of 1.5 liters of fluid which weighs 5.5 newtons. That is the question. So if we go to the solution, the first thing that you do is write down the given information. So we find out that your V, or volume, is equal to 1.5 liters. We find that the force is equal to 5.5 newtons, and we need to find the specific weight, we need to find the density, we need to find the specific volume, and we need to find the specific gravity of that specific liquid that we're working with. So we say that your volume is equal to 1.5 liters. Liters is not a fundamental unit of your volume. We know that the fundamental unit for volume is equal to cubic meters. So we find out that there's 1,000 liters is equal to 1 cubic meter. So therefore 1.5 liters would be 1.5 times 10 to the minus 3 cubic meters. That simply says that for 1 liter we need to divide 1 by 1,000, and then we multiply it by 1.5. So that would give us then the volume in terms of cubic meters. And so for the first one, we say that your specific weight is equal to the weight of the fluid divided by the volume of the fluid. Now the weight, force is a weight, so therefore that will be 5.5 would be the weight of the fluid. The volume would be 1.5 times 10 to the minus 3. So if we put that into the calculator, we find out that our specific weight is equal to 3666.66 newtons per cubic meter. Please do remember that for fluid mechanics or hydraulics, we work to 3 decimal places. So 3 places after the decimal, right? So that is 3666 point or comma 667 newtons per cubic meter. So the first one is answered. The second one is the density. And so we know that from the previous slides, we saw that the specific weight is equal to density multiplied by gravity. So therefore your density is then equal to your specific weight divided by gravity. And we find out that we have calculated the specific weight earlier. So the specific weight divided by your gravity, and we will always be using gravity is equal to 9,81 meters per second squared. So always in the equations we will use 9.81. So if we divide the two, we find out that our density then is equal to 373.768, 3 decimal places again, and the unit for density is kilograms per cubic meters. So now we've completed the second one. The third one is the specific volume, and we said that your specific volume is the inverse of your density. So that is specific volume is 1 over your density, and we get an answer of 2,675 cubic meters per kilogram, and again 3 decimal places after the comma. So the next one is your specific gravity, which we didn't look at previously. So we know that your specific gravity is equal to your density of the fluid divided by the density of water. So the density of water we will be using as 1,000 kilograms per cubic meter. That is under standard temperature conditions. So we will be using 1,000. So please do remember what I have written here. These are information that you need to know. You will not be given this information in any assessment, right? So we look at those details that we have there. So if your specific gravity is the density of the fluid divided by the density of the water, the density of the fluid we had calculated as 373.768 divided by 1,000. So the specific gravity is 0,374. Now please do remember that is dimensionless. There's no unit to it because we're having the density of the fluid divided by the density of the water. So it's a ratio between two densities, and so therefore the unit then is dimensionless. Right, so that concludes then the first question on page 25. And what I want you to do is to complete questions 2 to 8 for the rest of the session. And then by this evening, you can contact me on the WhatsApp, and then we will see where you got stuck with the rest of the questions. I will send a snapshot of the questions through to you because I do know that none of you or very few of you have the textbook. So enjoy the rest of the session. Do not sit idle. Try and work through question 2 to 8 for the rest of the session. On Thursday, we will be looking at chapter 3, which deals with the static pressures or hydrostatic pressures on surfaces. That is for Thursday.